In Chapter 6, we're going to tackle applications of integration, starting with general formulas for finding areas. We're going to look specifically at areas between curves. All right. So generally what we're going to have here is two functions of x, or we'll see later perhaps two functions of y. The region here, S, we could describe using set notation as all the points x, y, where x lies between the two numbers a and b, and the y values lie between two curves which are functions of x. All right, so f of x, g of x is on the bottom, that's less than or equal to y is less than or equal to f of x. All right. Sometimes a region like this is called a y-simple region. Now that's not vocabulary you need to know right now, but for those of you going on in calculus, it's going to come back in a while. All right. A y-simple region is a region in the plane which lies between two functions of x, up and down, and is bounded on the left and right by numbers. And we call it y-simple because it's simple to chop this thing up by taking slices that are parallel to y. Right? Look, if you tried to take slices that were parallel to x, right, in some places we would have different boundaries. Here we would have a boundary that's a line on the bottom and a curve on the top. Here we'd have a boundary that's a curve on the bottom and a line on the top. All right. But if we take slices the other direction like so, it's simple because these are simple slices that are parallel to y, so the name y, and it's y-simple because it lies between two curves that are functions of x. So we have an easy up and down boundary that's consistent for the entire region. All right. How do we find the area of this region? Well, like we did with so many integral problems, we're going to treat this as, we're going to start by approximating with a sum of areas of rectangles. So we're going to take our interval from A to B and chop it into some subintervals. It looks like here there are 1, 2, 3, 4, 5, 6, 7, 8, 9 subintervals. Right? So on each subinterval, we'll approximate the area between the two curves by an approximating rectangle. Right. And we do that and then add these 9 together and we get a good approximation of the area S. If we want a better approximation, we let the number of rectangles increase. Right. So let's look at one such rectangle, one of the 9. All right. So this one we'll say is the ith rectangle. In our picture here it corresponds to the fourth one, but it could be I equals 1, 2, 3, 4 up to n. All right. They're all going to have equal width, so we say that width delta x is, well, be b minus a over n, but that's not super important here. And how high is this rectangle? How much area is in it? Well, we have a top boundary and a bottom boundary. All right. So to get the height of this rectangle, we need to pick a point somewhere in the subinterval. We'll call that point xi star, and we're going to evaluate our function, our top function at xi star, that gives us this height, our bottom function at xi star, that gives us this height, and when we take the difference, right, we get the height of the rectangle. So the area of the rectangle is height times base, or base times height, I just wrote it funny, right, is the height times the width. Okay, so that's the area of one rectangle. We could call that area I. All right, and to get the area of the region, or the approximate area of the region, we need to take the sum of all these approximating areas. So that should give us the approximate area. And if you actually had to work out one of these, you could use midpoints, you could use left endpoints, right endpoints, the same as we've done in the past. The only difference here is what we're doing is adding up the height times the width. Instead of just a single function value, to get the height, we're going to take the difference of two function values. Now if we want the actual area, we need to let the number of rectangles, so notice I'm using equals here, because now this gives us the actual area. If we let the number of rectangles increase to infinity, right, And if you remember the definition of the definite integral, this is the same as the integral from a to b of f of x minus g of x dx. Right. So this gives us a recipe for computing the area of a y-simple region. All right. The y-simple and x-simple, it's not so important you remember those. All right. Y-simple means that it lies between, we slice it parallel to y. The area, the region lies between two curves which are functions of x. All right, let's work in an example. All right. So this is just summarizing the definition what we worked out on the last page, that if we have a top curve and a bottom curve, so f is above g, right, that we can find the area of this region by taking top minus bottom, and integrating from left to right. Right. The way I often remember these, in fact, is I will just write the integral from left to right of top minus bottom. Okay, that gives me the height times the width. Right. So this represents the sum from left to right of the height times the width, which gives me the total area. Right. For this, let's find the region area of the region shaded light blue here. So the integral from left to right, so 0 to 2 of top minus bottom dx. Now this is a relatively straightforward antiderivative problem. I'm not going to work it out completely for you. Well, let's go ahead and do it, I guess. Just see one example clear through. All right, so the antiderivative here, right, you can do a u substitution, or if you've gotten reasonably good at these, you can probably just spot that this is 2/3 x plus 2 to the 3/2 minus the natural log of x plus 1. Okay, so there is one antiderivative. I don't need plus c in the definite integral context. And I'm going to evaluate this for x equals 0 to x equals 2. So plugging in 2 and 0 under the first one here, I get 2/3 times 4 to the 3/2 minus 2 to the 3/2 minus the natural log of 3 minus the natural log of 1. Natural log of 1 is 0. So 4 to the 3/2, this means 4 to the 1/2 cubed, so that's 8. 4 to the 1/2 is square root 4. 2 cubed square root, so that's the square root of 8. So the rest of this, if you wanted to get the answer in the back of the book, you would do a little cleanup. Right, it's easy to check with your calculator that this is indeed a positive number, right, and it represents our shaded area here in the picture. All right. That's the easiest kind of problem. When the region is well defined, they tell us what the top and the bottom are and what the left and right values are. Not all the problems are quite so simple. All right. Sketch the region here enclosed by these two parabolas. I know they're parabolas because they're quadratics, and find its area. Y equals x squared. Well, we should be pretty familiar with that one. Oops, and I did a lousy job of drawing it. But I'm supposed to go through the origin here, so we'll make the origin fat. All right, and y equals 4x minus x squared. Well, that's y equals 4, let's see, x times 4 minus x, if I factor out an x. So I can see there's a 0 at 0 and a 0 over here at 4. Okay, and so that's a upside down parabola. I know it's upside down because I have negative x squared. All right, so the region in between these curves goes from here to here. It looks like the left end of this is at 0. Where's the right end right here? Okay, I'm going to take top minus bottom from left to right. To find the left and right ends, for sure, I need to set these two equal to each other and solve for the intersection. And that's a general idea that you're going to see over and over in this section. So I set them equal. Okay. Trick here is move everything to one side. Factor if you can, quadratic formula if you can't. So I see x equals 0 or x equals 2. So x equals 0 corresponds to the left end, x equals 2 corresponds to the right end. Right. The top curve minus the bottom curve. Right. So the area here of the shaded region is the area from left to right, the sum from left to right of the top from left to right, top minus bottom dx. Now, a little simplification, and then you work out the integral. So 4x minus 2x squared dx. Notice here that what I'm looking at here, the difference between the two curves, is something that I've encountered already in this problem when I went to find the intersection. That happens a lot, so you should see some familiar things popping up there. All right, I'll let you work out the details of this definite integral. All right, this problem looks a little different, but it's exactly what we were doing before. It's just turned sideways. All right. This region is sometimes called a x-simple region because it's easiest to slice up this region, if you're thinking of approximating rectangles, by going from left to right. Right. So if I were to describe this region, let's give it a name S. It's the set of xy points where y goes up and down between 3 and 0. So now the limits on y are numbers, and the limits on x are these two curves. We have a left curve and a right curve. Now to find the area, we're going to basically just do exactly what we have done before, except we're going to reverse the x's and the y's. If that's a problem for you, just turn the picture sideways. All right, now we have a top and a bottom. Okay, it looks very similar. All right. So the area of the region S is going to be the integral from bottom to top, okay, of the right curve, which is a function of x, minus the left curve, which is a function of x, dy. So the bottom is 0, the top number is 3, the right curve, and I did this, the right curve is a function of y, and the left curve is a function of y. All right, the right and left curves are functions of y, and they give us boundaries for x. That's why we call this x simple, right? Because x goes between one curve, which is a function of y, to another curve, which is a function of y. My bad there. All right, so the right curve, right? The right curve is this one, minus the left curve, dy. Now clean that up and evaluate the definite integral, and you'll find the area of the shaded region. All right, last example. Find the area between these two trigonometric functions. All right, we've got here the red curve is y equals 2 sine of x, and the blue curve is y equals tangent of x. Okay, and the area in between these two curves has basically two components. Right. What makes this problem a little harder is that the top and the bottom curve depend on where you are. Over here we've got red on top and blue on the bottom, and vice versa on the left side. Right. But since we need the height to always be positive if we want to add these things up and get area, right, we either need to break this problem into pieces and use different tops and bottoms, or we can compactly write this by doing the following. We're going to do the integral from left to right of one curve minus the other curve in absolute value. And if we take the absolute value, it's always going to come out positive. So that represents the height, right, dx. Okay, so we've got an approximating rectangle, let's say right there. F minus g or g minus f, it doesn't matter because we're going to put an absolute value on it. Right. So in this problem, we're going to go from, well, wait a minute, what are these left and right points here? Looks like 0's in the middle here. I've got to solve to find where those are. Right. It turns out they're these, but let's see the math. Right. So I set tangent of x equal to 2 sine x. Move everything to one side. At the same time, I'm going to write tangent as sine over cosine. Factor out a sine. Right. So either sine of x is 0 or 1 over cosine x minus 2 is 0. That happens when cosine x is equal to 1/2, which occurs at x equals plus or minus pi over 3. All right. So the right end here is at pi over 3, the left end at minus pi over 3. So we're going to go from minus pi over 3 to pi over 3. Top minus bottom. Wait a minute. I don't know what top minus bottom is, hence I put in the absolute values. All right, I will take 2 sine x, and look at the red curve here on the right, minus tangent of x, and absolute value times dx. All right. Now there are two ways to go about doing this integral. One is to deal with the absolute value. All right. I'm going to have to split this into two. Okay, sorry that was glitching out there. All right, so we've got left and right, all right, and then the height, which is represented by the absolute value, the difference of the curves, times the width of each subinterval. Two ways to go here. One way is to deal with the absolute values by splitting the problem. And here we would have to split it at 0, so we would have the integral from minus pi over 3 to 0. All right. On that interval, from minus pi over 3 to 0, we can see from our picture that tangent is the top curve. So to make this positive, I'm going to take tangent of x minus 2 sine of x. That's the same as just adding in a minus sign. Plus, from pi over 3 to 0, or 0 to pi over 3, we've got sine on top and tangent x on the bottom. So we could work those two separate integrals. But an even more clever way to go is to use symmetry. Right. These are both odd functions, and the area to the left here is the same as the area to the right. So I just need to compute one of those and double it. So we're going to go with the right side. And we get 2 times the integral from 0 to pi over 3 of 2 sine of x minus tangent x dx. So now find an antiderivative and evaluate the definite integral. Minus 2 cosine x minus the natural log of the secant of x. That's one of those weird ones. And I need to evaluate that from x equals 0 to x equals pi over 3. And if you finish that evaluation, that'll give you the area of the region between the two curves.